This is joint work with folks at UVM, and this is my first USENIX, and I'm really excited to be presenting my work here. So ready to jump in. So I hope I don't have to convince anyone that platforms matter. They mediate interactions between human users. And so platforms provide critical infrastructure for businesses and social systems. And so any changes that occur on those systems matter. And these changes might have implications for firms and end users. So I'll give a couple of high-profile examples. A couple years ago, Google changed their logo to save space. And so less space is great for everyone. More recently, Instagram changed their content serving algorithm to favor more video content. And this meant that artists that use Instagram to contact their audiences had to change their business model overnight. And so this was not great for content creators. A couple weeks prior to that change, there was a report that Facebook had considered changing its algorithm to compete with TikTok. And so when these changes are put onto systems, these are usually an intervention with some sort of expected result. And for many changes in software, these may be possibly imperceptible or may have many types of effects, and these things might be hard to predict. So the question is, how to decide what to change? And so the answer is to perform experimentation. And so we can consider a couple of different experimental contexts. You might have a laboratory experiment, for example, a university psychology lab, or a field experiment, like a platform in the wild. And in these systems, there's information asymmetry by design. This asymmetry exists between the participants and the experimenters. So I'll give a little more detail here. In general, there are three pieces of information you might be interested in if you're in an experiment. I want to know if I'm in the experiment, the experimental condition that is being applied, and I might want to know the outcome of interest. And so if I'm an experimenter, I get to know all of these things. But if I'm a participant in the experiment, there are reasons to shield the participants from these particular pieces of information to reduce bias in the estimates. And so the asymmetry is sometimes necessary in the design of the experiment, but it turns out participants don't like to feel like they've been deceived. And so this may lead to some forms of non-cooperative behavior. I can provide a bit of anecdata on this. So this is a screenshot from my Facebook back in 2015. This is right after they introduced their new emojis. And there's an article here posted that suggests how Facebook wants to use this new emoji data. And this particular user says, the only appropriate way to deal with this is to use the wrong emojis for each situation, which I plan to do from now on. And so back when I started this work in 2015, I work in machine learning, and the general reception was that this is primarily a theoretical question, not a real issue. However, fast forward to 2017, and there was evidence of adversarial behavior in the 2016 US election. And meanwhile, there's also experiments running on Facebook for several years to increase voter turnout. So this has implications for these particular experiments that have been running since 2010. So we identified this model of non-cooperative participation. We define a non-cooperative participant, or NCP, as an individual in the population who responds under an intentionally different response model than their true outcome when they're in an experiment. Our work is the first to define this behavior with respect to online experimentation. So what does this mean? So we have an individual, and if we're running an experiment, then we have some treatment that we're interested in. We'd like to measure the effect of that treatment on some outcome of interest that pertains to the individual. And so that individual's behavior may influence that outcome in some way. And that their behavior may be influenced by their belief that they're in an experiment or their values. And these are both hard to measure, so they are represented by these dashed lines. And their beliefs and values may also be influenced by external information, which we may have some access to. For example, knowledge of news articles or research on the use of experimentation on platforms. And so the user or the participant may also provide statements that imply their intent to not cooperate. For example, this user on Facebook. So what do we do about all this? Well, I'm from machine learning, as I mentioned, and so we like to throw math at the problem. And the idea is to correct for statistical bias in the estimator of treatment effect. But how we do that depends on network structure assumptions and the conditions of the experiment. And this really grounds out into two different contexts. The propositional setting, where users and participants can't influence the effects of the outcomes of other participants, and the relational setting, where participants' outcomes may influence the outcomes of other participants. In the propositional setting, if I have only a small number of NCPs in my population, this may induce a small amount of noise in my estimate, but I may not be too concerned about the presence of these participants. However, if there's a large number of these participants in my population, then I may be concerned about bias that's induced by their behavior. However, if I have access to something like a statement that it signals intent to participate in this way, then I can remove all of the non-cooperative participants and retain my unbiased estimate of the outcome of interest. So in the propositional setting, there's a high overhead of NCP coordination to induce bias. And we can compute unbiased estimates by removing known NCPs from the population. In the relational setting, I'm concerned about, researchers are concerned about the spillover of treatment to other nodes that may not be exposed to treatment. And in the relational setting, estimating individual and peer effects is a well-studied problem. This is typically accomplished by clustering the network and using a cluster-based randomization design to assign treatment to all nodes in a particular cluster. In this work, we study estimates of average treatment effect, which is the overwhelmingly common model of estimation in social science and econometrics. However, this design does not account for non-cooperative behavior. In particular, there may be spillover of a similar form, but of NCP behavior to the behavior of neighboring nodes. So, users may alter their behavior in response to the expectation that they're in an experiment. Users may interact with others who are also in the experiment, causing estimates of treatment effect to be tainted by spillover or peer effects. And NCP behavior may propagate in the network via peer effects. If I simply remove the NCPs that I might be aware of, like this dark node in the center, that doesn't account for the additional bias through the observation of that outcome by neighboring non-NCP nodes. To study this, we conduct a bias analysis. And in particular, we study the effects of NCP location in the network. We study the greedy condition, where NCPs must form a dominating set, meaning that all nodes in the network are exposed to at least one outcome from an NCP. And we also consider the random case where nodes are selected uniformly at random to be non-cooperative participants. In the experimental design for our simulation studies, we consider two critical design choices. These are the network structure, which informs how participants are connected, and the outcome simulation, which informs how participants respond to treatment. For network structure, we consider both synthetic and empirical data. We use synthetic graphs generated to replicate community structure, and we consider also a real-world social network subgraph. Our outcome simulation model is drawn from prior work, and we also use a non-cooperative participant model that minimizes the effect of treatment. In our synthetic simulations, we find that bias induced by NCP behavior increases linearly in the number of non-cooperative nodes, and that greedy placement generally results in higher bias than random placement, especially for large peer effects. The main takeaway here is that relational context amplifies NCP bias. So I'll zoom in on one of these particular results. If there was no bias induced by the NCP behavior, then we would expect the orange lines to be horizontal. And instead, we see that there's an increase as we increase the number of NCPs, and this increase is much larger for the greedy selection procedure. We've talked a lot about Facebook, but this happens on all kinds of social platforms. And so the implications here, because community structured networks are particularly vulnerable to bias from NCP behavior, this is what we've shown in our experimental results. And this is a real problem unaddressed in the research community for online experimentation. We provide a statistical correction, however, this correction is not enough. The correction simply removes the outcomes for NCPs and participants that are exposed to NCP behavior. And you need more than math. As future work, we can study alternative experimental designs that are more robust to such behavior. And in particular, we hope that systems community researchers can help design better systems for protection of end users. In summary, community structured networks are particularly vulnerable to ATE bias from NCP behavior, and we need creative design solutions and experiments in software systems, not just mathematical corrections. Thank you.